Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 5, Part 1, Ideal Gases. This is lecture number 8. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bangalore. So we will continue to solve numerical on gas mixtures. So we will solve this problem number 7. The mass analysis of a gas mixture shows that it consists of 60% of nitrogen, 30% of carbon dioxide and 10% of CO. If the temperature and pressure of the mixture is 20 degrees Celsius and 3 bar, compute the partial pressure of the components, molecular weight of the mixture and gas constant for the mixture. So here you know the equation for the gas constant of the mixture as the mass fraction into gas constant of individual constant elements added for the all the constants together. So also you know that this Rm, that is gas constant for the mixture, is nothing but R bar by molecular weight of the mixture. Similarly, mass fraction of N2 as it is, and gas constant for nitrogen is nothing but R bar by Mn2. Similarly, RCO2 is R bar by MCO2 and here R bar by MCO. So from this you will get molecular weight of the mixture MM is equal to 1 by MfN2 by Mn2, MfCO2 by MCO2 plus MfCO by MCO. So if you substitute, so you will get the molecular weight of the mixture as 31.429 kg per kg mole. You see, this is one solution. Suppose if you have any alternate ways to solve this problem to find out molecular weight of the mixture, so surely you can find out. There is nothing wrong. Now Rm is nothing but R bar by molecular weight of the mixture, so you will get it as 0.2645 kilojoules per kg per degree Kelvin. Now if you consider 1 kg of the mixture, so the number of moles of mixture is mass of mixture into molecular weight of the mixture, so you will get 0.0318 moles. Similarly, the mole fraction is nothing but the number of moles to the ratio of the number of moles to the of the individual constant gas to the number of moles in the mixture. So here again this Ni is nothing but Mi by Mm, so divided by Nm. So if you substitute here, so you will get it as mole fraction of N2 as 0.6. Similarly, mole fraction of CO2 you get it as 0.3 and mole fraction of CO you get it as 0.1. Now coming to the partial pressure, so here it is pressure of partial pressure of N2 by total pressure of the mixture. This is nothing but the mole fraction. Okay, so from this you can find out the partial pressure of N2 as mole fraction into pressure of the mixture, which is 3 bar, so you'll get as 1.8 bar. Similarly, you can find out the partial pressure of CO2 as 0.9 bar and partial pressure of CO as 0.3 bar. To solve this problem, a tank of 0.7 meter cube capacity contains O2 at a pressure of 5 bar and 320 Kelvin temperature, and N2 is introduced without change in temperature until the pressure in the tank becomes 8 bar. Determine the mass of each gas in the tank and partial volume of each gas. So here this is a filling here. A tank of 0.7 meter cube capacity contains O2 at a pressure of 5 bar and temperature of 320 Kelvin. Now we are introducing nitrogen without change in temperature until the pressure in the tank becomes 8 bar. So you have to find out what mass of nitrogen is introduced into the tank and what is the partial pressure volume of each of this gas. So here Vm, okay, this is equal to here missing. Vm is equal to 0.7 meter cube. Partial pressure of O2 is 5 bar. Temperature is 320 Kelvin. Total pressure, that is mixed pressure of the mixture, is 8 bar. You have to find out mass of O2, mass of N2, volume of O2 and volume of N2. Now we have the state equation PO2V is equal to MO2RO2 into T. Similarly, for nitrogen, we have PN2V is equal to MN2RN2 into T. Now, you know that the total pressure of the mixture is nothing but the summation of the partial pressure of oxygen and the nitrogen. So here, the partial pressure of nitrogen, if you substitute here, because PM is 8 bar and PO2 is 5 bar, so you can find out the partial pressure of nitrogen as 3 bar. Also, you have the state equation PMV is equal to MMRM into T. Now, from this you can write the ratio of the partial pressure of oxygen to total pressure of the mixture. The ratio is nothing but the mole fraction by O2, which is also equal to volume fraction VO2 by Vm. Now this is already calculated as 0.625. So by from this expression you can find out volume of O2 as 0.625 into the total volume of the mixture, that is Vm here. Okay, that is 0.7. So you'll get it as 0.4375 meter cube. Similarly, you can find out volume of N2 is 0.2625 meter cube. Now you can observe here, if you add these two volumes, that is volume of oxygen and nitrogen, so you'll get the total volume of the mixture, that is 0.7 meter cube. Okay, that is very, very important here. Now using the state equation PO2 VO2 is equal to MO2 RO2 into T. So here RO2 is nothing but R bar by MO2. If you substitute this for RO2 and if you rewrite the expression, you will get the expression for mass of O2. So that you will find it as 2.631 kg, and similarly mass of N2, if you substitute, you will find it as 0.8288 kg. So this is one of the things asked to be found out, that is mass of oxygen and the mass of nitrogen, especially the mass of nitrogen introduced into the tank. Okay, now we will solve this problem. A gaseous mixture contains 21% by volume of nitrogen, 50% by volume of hydrogen and 29% by volume of carbon dioxide. So this is nothing but the volume fraction of these individual constant gases. So you have to calculate the gas constant for the mixture, the ratio of specific heats. If the mixture pressure is at 1 bar and mixture temperature is 10 degrees Celsius, calculate the partial pressures and mass fractions of the constants. So here I think this table is not required to be used. So directly you can you will know the values of molecular weights of nitrogen, hydrogen and carbon dioxide. So molecular weight of nitrogen is directly you can take it as 28, no need to take 28.02. I think this is taken from the table. So hydrogen is 2 you can take, and CO2 is 44 because carbon is 12, O2 is 32, it is 44. So if you know for the individual constant gas, you can find out the molecular weight of that. Okay. Similarly, from the table 11, now the table number may vary. So first one is the molecular weight table. This is the specific heat table. So specific heat for nitrogen is 1.039 and specific heat of hydrogen is 14.15 and specific heat of carbon dioxide is 0.818. I think this you have to refer from the table. No need to refer for the molecular weight because you can remember that. Now you are given the mole fractions, volume fraction sorry. So V of N2 is 0.21, which is nothing but volume of nitrogen to the total volume. Similarly, V of H2, which is nothing but VH2 by V, and similarly V of CO2, which is nothing but VCO2 by V. So this is given as 0.29. Okay. Pressure is 1 bar, temperature is 283 Kelvin. So here, if you want to find out the gas constant for the individual gases, so you can use this expression R is equal to R bar by M. So if you write for N2, you will get Rn2 bar is equal to R bar by Mn2. Similarly, you can write for RH2 and RCO2, and you will get the values of the gas constants as 0.297, 4.124 and 0.189 kilojoules per kg per Kelvin. Now, if you want to find out the specific heat of the individual constant gases, now you know that Cp minus Cv is equal to R, or Cv is equal to Cp by Cp minus R. So this is Cv is equal to Cp minus R expression. So Cvn2 is nothing but Cpn2 minus Rn2. So you get it as 0.742 CvH2 is nothing but 14.15 minus 4.124, you get it as 10.026, and CvCO2 is 0.818 minus 0.189, you get it as 0.629 kilojoules per kg per Kelvin. So we know that volume fraction is equal to mole fraction. So mole fraction of nitrogen is nothing but volume fraction of nitrogen, which is 0.21. Similarly, mole fraction of hydrogen is 0.5. Mole fraction of CO2 is nothing but 0.29, which are given in the question. Now you can use the molecular weight of the mixture formula, that is MM is equal to YN2 plus YH2 MH2 plus YCO2 MCO2, and if you make proper substitution, you will get the molecular weight of the mixture as 19.654 kg per kg mole. Similarly, gas constant of the mixture Rm is equal to R bar by molecular weight of the mixture. After substitution and simplification, you will get it as 0.423 kilojoules per kg per Kelvin. Now mass fraction of N2 is nothing but mass of N2 by total mass of the mixture. So here mass of N2 can be substituted as number of moles of N2 into molecular weight of N2. So here N2 by Nm, this ratio can be written as Yn2. So you will get an expression for mass fraction of N2 as Yn2 into Mn2 by Mm with the usual notations. So if you substitute, you will get it as 0.2993. Similarly, you can find out mass fraction of hydrogen as 0.0513 and mass fraction of CO2 as 0.6494. You see, here this is maybe one of the ways to find out the mass fractions. Suppose if any other alternate method is or way is available, so you can solve that also. So you can try, check for the answer, but answer will be same. Now for the mixture, the specific heat at constant volume Cv for the mixture is nothing but mass fraction of N2 into Cv of N2 plus mass fraction of H2 into Cv of H2 plus mass fraction of CO2 into Cv CO2. Since you know the values of CvN2, CvH2 and CvCO2, sorry here CvH2, CvCO2 here, so you will get the Cv for the mixture as 1.145 kilojoules per kg per Kelvin. Now also you know that the Cp of the mixture is nothing but Cv mixture, M should be there here, okay, Cv mixture plus R of the mixture, so you will get it as 1.568 kilojoules per kg per Kelvin. Now the ratio of the specific heat for the mixture gamma M is equal to Cpm by Cvm, so you will get it as 1.369. So mass of the mixture M is equal to, you can use the state equation PV is equal to MRT, so M is equal to P1 V1 by RT1, so it's up substitution, so you will get it as 0.07 kg. So with this I conclude this lecture number 8, and we'll try to solve few more problems in the lecture number 9. Thank you.